Okay, let's look at Theorem 10.2, properties of subgroups under homomorphisms. So phi is a homomorphism from a group G to G bar, and let H be a subgroup of G. That's the situation we are in. And again, since a homomorphism is a generalization of an isomorphism, we keep some of the properties of subgroups under homomorphism that we already encountered when we looked at the properties of subgroups under isomorphisms. So the first three, in fact, are things that we keep. So H is a subgroup, then phi of H is a subgroup of G bar. And if our subgroup in G is cyclic, then the image phi of H is cyclic as well. If H is abelian, then phi of H is abelian as well. So those are three results that we've already known for isomorphisms, and we keep them for homomorphisms. Then we have a few new things, because since we talked about isomorphisms, we've encountered some new ideas. So if H is, in addition to being a subgroup, if it's normal in G, then phi of H is also normal in phi of G. So we have this new property of a subgroup being normal that's also preserved under homomorphisms. Now, if the kernel of phi has order n, then phi is an n-to-1 mapping from G onto phi of G. So we saw that in the previous two examples, where every element that was in the same coset of the kernel mapped to the same element in G. And so we always had like several elements mapping to the same element in G bar, and it was always the same number, right? So we had two things mapping to the same element in G bar, and another two things mapped to a different element in G bar, and another two elements mapping to the same element in G bar. So here we have G, here we have G bar, and so we have this 2-to-1 mapping. We saw that in example 3a. And then we had a 5-to-1 mapping in example 3b. Property number 6 says if the order of H is n, then the order of phi of H divides n. Again, since we don't have a 1-to-1 mapping anymore, we don't keep that the orders of a subgroup and its image have to be equal. We just keep that the order of the image divides the order of our original group H. And then we have two important properties that we're going to talk about in a little bit more detail. If K bar is a subgroup of G bar, so if we have a subgroup in our image group, then the inverse image of that subgroup is also a subgroup of G. So we had the similar property, number 1, that if H is a subgroup, then phi of H is a subgroup. It also works the other way around. If K bar is a subgroup in G bar, then the inverse image is a subgroup in G. And same thing with normal. So if K bar is a normal subgroup of G bar, then the inverse image is a normal subgroup of G. And then our last property is that if phi is onto, and the kernel of phi is just the identity, then we have an isomorphism again, because then we have a 1-to-1 mapping. And really, that's the only thing that we lost when we went from isomorphism to homomorphism. So if the kernel of phi is just the identity, then phi is an isomorphism from G onto G bar. Properties 7 and 8 have an important corollary. So there's an important corollary here. And that is that the kernel of phi is a normal subgroup of G. So in symbols, that is kernel phi, and then we have our triangle symbol for normal subgroup G. so is normal in G. And that is pretty straightforward to prove. So I'm going to do the proof real quick of that corollary. So number 7 says that the inverse image of a subgroup is a subgroup, and the inverse image of a normal subgroup is a normal subgroup. And so if we can write the kernel as the inverse image of a normal subgroup in G bar, then we are done. So, and that is not that hard to do. So let's look at K bar. That as inverse image will give us a kernel. Well, what's the kernel again? The kernel of phi is all the elements in G that map to E. So it's really the inverse to E bar, since it's in G bar. So the inverse image of E bar is the kernel. And the subset only containing the identity in G bar, that is a normal subgroup of G bar. So there is our normal subgroup in G bar that has the kernel as its inverse image. So the kernel of phi is the inverse image of this subgroup K bar, and therefore it's a normal subgroup in G. And that's really it. So this is by theorem 10.3.8, property 8 in our properties list.